Okay, so this is an example midterm problem that's actually out of scope for the first, for this, sorry, second midterm. Um, but it's not out of scope for the final, so we do need to understand kind of these types of problems. Okay, so this is kind of a good combination problem because we're dealing with conservation of momentum and kinetic energy. Sorry if I'm kind of heavy breathing in the mic here. If you're listening to me drink coffee, very exciting. Um, okay, so let's kind of talk about what's happening in this problem. All right, so we have a rod and there's a length of the rod. So L is the length. It's also the radius kind of this system because if this is the point that it's rotating around initially. Okay, so there's a rod with length L and then there's this little mass that's super tiny. It's like right here. It's mass M, right? Rotating, oh, sorry, mass M. Sorry, the big rod has mass M. And then the small point mass, little m, this guy is equal to big M over 4. So normally if you see like where they give you this algebraic relationship where they relate the masses, at some point they want you to use algebra to cancel it. So sorry, but it's a good hint. Okay, so all right, we blah, 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 point mass. So there's an initial velocity, V naught, that the point mass has. So mass has a V naught, and then it collides elastically with the rod. What does elastically mean? So, good question. So when we dealt with linear momentum, so if a collision is totally elastic, they just bounce off of each other, and all the energy is conserved, and so they collide with some initial velocity for both of them, and then they go in opposite directions with some different velocity for both of them. Okay, but the momentum from the beginning and then the momentum at the end after they bounce off is going to be equal. It's just redistributed basically. Okay. So we know that Li is equal to Lf. Why is this angular momentum? Well, this thing is like spinning around in a circle, right? This guy is linear, but this thing is spinning around. Okay. So, all right. After the rod, after the collision, the rod stops rotating. Okay. So all of the energy from the rod is like converted and given to this little dot here that's just sent off flying. And the point mass moves in the opposite direction with the velocity v. The point mass ends up going in this direction, right? With some velocity v, okay? And we want to know what v naught is. Okay, express your answer in terms of L and W. Okay, so we have Li is equal to Lf. Okay, so let's look at some general things. So in the beginning, so to figure out what's going on in our system, we want to look at kind of what has velocity. So this is kind of weird because we have something moving linearly and then something rotating. So we want to relate the tangent velocity and the rotational velocity, basically. So Li for our system, we have IW, right, for the rod, okay, plus some mass times velocity, right? So plus some m, right, times r, this like the r distance basically. So we'll say m times l, right? Because that's what it would be away from the circle. Because it's so close to that rod that we can kind of like model the velocity around the same radius. We're just going to treat it as like a tangent velocity. That's basically moving around that circle because it's like almost adjacent to that rod. So we have ml, and then we're going to say that we have this velocity, right, that's moving tangent to the circle. So we're gonna say that it would have some angular acceleration theoretically if it was spinning around there, but we can model it as v over r, right? We're just modeling it as this instantaneous tangent velocity to the circle. Okay. This might be a weird assumption for some of you guys, but okay. So when we do so, right? Okay. So we're treating it as a point mass, right? And so I of a point mass. Sorry, this is L squared. I have a point mass. is going to be equal to mr squared, right? And that's what we're going to use here. So we have some point mass, right? And then we're going to, for our w, for the point mass, we're going to use the tangent velocity over r. And then the tangent velocity is going to be the initial velocity, basically, that they have for this guy. So that's going to be some v naught, right? Okay, over L. Okay, v naught over r. So we have IW of the rod, right? I of the rod, W of the rod, and then this guy, the second one is for the point mass. So that's everything initial in our system, right? We have this angular momentum for this rotating rod, and then we're modeling this angular momentum right here, right, for this V naught for this little small point mass, right? The small point mass with a V naught. Okay, so then what's happening at the end of our system? Well, LF for our system, our final piece here, same thing, right? We have L squared, but then we have some final velocity, right? V over L, where it's just bouncing back in the opposite direction. And this is going to be negative, right? Going in the negative direction, okay? So we're just modeling it as kind of like a tangent point on this circle, okay? So this is our final, this is our initial, okay? So we're going to set our initial equal to our final here for conservation of momentum at this particular point, okay? So say for Li equals Lf, I'm going to go ahead and do that. So I W times W rod. I'm just putting the subscripts to kind of tell you what these belong to. Then mass, the little point mass, I'll plug that in right now. M over 4, right? Because we were given that for the little m. And then L squared divided by L is just going to be, we're going to have one L and then a V naught, right? So just simplifying this a little bit. This is the Li from up there, right? And then LF, we have negative MLV, right? Just canceling out that extra L. And this is our LF. Okay, so if we set these two equal to each other and we do a little bit of algebra here, let's see what we have for our V relationship here. So IW for the rod, we know that for a rod, or not IW, sorry. I don't know where IW, IROD. So IROD is going to be equal to 1/3 ml squared, right? Because it's just the mass moment of inertia for a rod. So 1/3 ml squared, and then we'll plug in the big M over 4, right? And then we have W plus M over 4 times L. V naught is equal to, well, negative big M over 4, right? L times V. Okay, well, we've got a lot of L's going on here. So let's cancel quite a few things here. Let's cancel all of these masses. Let's cancel all of them. Over 4. We can't cancel M over 3, but we can cancel the M, right? M over 4 squared. Yeah, so we're going to end up with, I think we just canceled the M's. I think we're going to have to keep the fractions in there. So let's cancel all of the M's, and then we're going to have 1/3 L squared. Let's cancel all the L's actually, or some of the L's. 1/3 L, W plus, so I'm just taking out the M's. So let's cancel the M's. And I'm going to cancel this L, and then this L squared. Okay. Plus 1/4 V naught equals negative 1/4 V. So multiply everything by 4, and then we're going to have 4/3 LW plus V naught equals V. Okay, so we've got kind of a relationship here. So that's as far as we can go using conservation of momentum. But the problem wants us to figure out V naught in terms of L and W. So we have L, W, and V. So we need to figure out a different expression where we can get a value for V and do some more math, basically. Kind of almost running out of time here for this section. So I'm going to try to see if I can just get through this final problem here. Sorry, for some reason, my iPad time, every time I do screen recording, it always just says 9:41 and it like won't change for some reason. I think you guys probably noticed that by now. I don't know what is going on with that. It's very weird. Okay. All right, so let's talk about energy for this system. What the hell is going on with energy? So like we talked about before, when we have energy in the system, what do we care about? Where are our velocities for the kinetic energies, and what's our change in height? For this problem, the whole thing is kind of happening at the same height. So everything is sort of like along, do a dotted line here. Everything is sort of like along this line here, right? We don't have any change in height. We don't really have any change in potential energy. Um, we're kind of treating it all as like this instantaneous point collision at the top of the circle, okay? So the system is essentially rotating, but like at the instantaneous point, that's where we're modeling stuff. Um, but we don't have any change in H in between the collision, right? So EI, EF, okay. So what are all of the energies? So initially, so let's say delta PE, 0, and delta KE. So we'll do them for both, right? We're kind of going to do a table here. Okay. So our KE for both of these, we have a linear velocity from that little guy that's moving, right? And so the linear velocity, we know, so for KE or linear or translational, 1/2 mv squared, this is the general equation. And then for KE rotational, the general equation is 1/2 I w squared. We saw that in the table when we first started in the section. If you skip that part, feel free to go back to it or just look at the equation sheet that I post in Canvas or your book or whatever you want. Totally fine. So, okay. So I know that I have the kinetic energy from that little point mass moving, and I have the rotational kinetic energy from that big bar that's moving. So I'm going to put those both in there, right? So let's do the bar and the point mass. Okay. Can I move things over anymore? Maybe I'll just make it a little bit smaller. I can zoom for you guys. All right. Okay. So for the kinetic energy here, for the first one, so for the little mass, I have 1/2 little m, right, v naught squared, because that's what we start with for the initial. And then I am adding 1/2 I of the rod, right, times w squared. Okay, cool. So then for EF, I have, for the final velocity, I have 1/2 mv squared, right, for the final. Okay. So let's go ahead and set EI equal to EF, and we're going to sub M is equal to big M over 4. And let's see if this equation lets us get a second equation that we could use to like simplify this first one so that we can get just isolate V naught and get it in terms of L and W. So we have like L and W here, right? But we still have this V term. So we could rearrange things for this guy, but we want to just solve for V naught and get rid of this other V. So let's see if we can find some expression for V using EI equals EF. EI equals EF. Okay, so I'm going to set these guys equal. So 1/2 M over 4, right? Just taking this piece right here times V naught squared plus 1/2. And then I'm going to plug in I for the rod. So what was I for the rod again? 1/3 ml squared. Ml squared. And then times w squared. W squared is equal to 1/2 mv squared. Okay. Oh, sorry. M over 4. Big M over 4. Okay, cool. So let's simplify some stuff here. So we can cancel out our m's. Everything's multiplied by m. I think that's the best we can do there. Right. Okay. So then we're going to end up with, and move some other things around. Let's multiply everything by 2 also, because everything is multiplied by 1/2. So we end up with 1/4 V naught squared plus 1/3 L squared W squared is equal to V squared. Okay. All right. Did I cancel out something weird? Because I think they did something a little bit different. 3rd, 4. Oh, rotational W. I think I might have a little, I'll write their final equation. I'm I'm sure that I probably am the one who has like something weird going on here. Oh, wait. Yes, sorry, 1/4. Yep, that's what that is. Okay, so, all right, now I'm gonna multiply everything by 4. So that just, only one term has a constant on it. Third squared w squared equals v squared. Okay, so now I have a second expression, and this gives me what I need. So I have a second expression, and I can put in my v is equal to that. And it's going to be a huge pain, actually. Yeah, so you're going to need to use the quadratic equation to solve this. I'm going to leave the rest of that because that's just basically sort of like some busy work math here, and I only have 3 minutes left. So it's pretty step by step on the sheet there. I think that it's pretty straightforward. I just don't know if I have time to write all out in 3 minutes. Okay, so the final answer, so you do need to use quadratic formula. Or just some creative algebra here. But the final answer that you're going to get is V naught is equal to 1/6 WL. Okay. Yeah, I'm trying to think of the way that I can quickly do that. No. Oh, solve quadratic equation. You don't have to use quadratic formula. This will be quick. I'm going to do this. Sorry, I'm misreading my own note. Okay, so let's go ahead and just plug everything in here. So let's set this v is equal to v naught squared. We're going to just kind of like solve for a bunch of stuff here. Okay, so we're going to say v naught squared is equal to v squared, right, minus 4/3 L squared W squared. This is not going to be too bad, just a little bit long. So, but a lot of things you can just like algebra it all together and it's going to be okay. V naught squared minus 4/3 L squared W squared. So I just sort of peeked ahead to try to see what it was doing, and I was like, do I have time to do this? And I thought no, but I think we'll make it. Okay, so then we're going to say v naught squared is equal to, if we expand this whole term out here, we're going to have, right, like 4/3 LW times itself, 4/3, just foiling this, right? First outer inner last, plus v naught times 4/3 LW, and this will be times 2. So it's just foil here, right? Plus v naught, oops, v naught squared minus 4/3 L squared W squared. Okay, let me just check to make sure that I'm, doing things right to here. 8/3. Okay, so then if we can cancel out this v naught, right? Because we have it on both sides. So cancel this. We're gonna move some stuff around. So then everything is times. So 4/3 L squared. Page. This is a little bit ambitious with the time I have left, but oh, sorry, I added a page in the wrong place. That was not helpful. Okay. If you want to just kind of skip ahead to the answer and I'm boring you to death, please feel free. L squared W squared. I'm sorry, this 4/3 needs to be squared as well. So we're gonna have 12/9, right? Oh wait, sorry, squared. 16 ninths. Duh. Sorry. 4 squared is 16. Yep. Minus let's see, 8/3 v naught LW minus 4/3 L squared W squared equals 0, basically. So yeah, so we can combine things a little bit more here. So bring these terms together. We're going to end up with basically, when we group these, I'm going to skip a little bit. So yeah, we're going to end up with, sorry, 4/3 WL. Well, should I call this here? Okay. When you have 0 on one side and you want to divide things, it's actually very nice because you can simplify quite a few things. So let's say that we divide everything by W here. So let's say like if we 16/9 L squared W squared minus 8/3 V naught LW minus 4/3 L squared W squared. So we're going to divide everything by LW basically. So we're going to have 0 divided by LW, right, is equal to 0. And then this whole thing divided by L times 1 over LW. So nice trick if you have 0 on one side. 0 is equal to 16/9, right, times LW minus 8/3 V naught minus 4/3 LW. Then we can combine these two terms, right? So we're going to end up with 4/3 LW, right? Sorry, 4/9. Sorry, I'm skipping one more step. So 4/9 LW is equal to 8/3 V naught, and then V naught is just equal to 1/6 WL. Okay, so I'll leave you guys to do the last fractional piece there. Okay, so yeah, so there's our step-by-step there. Okay, so just to summarize, that was very math dense kind of at the end, and I feel like sometimes when we get lost in the weeds with the math, the general concepts get lost. So I'm sorry if you just watched me do all that math. But basically, the takeaway here. So what we're doing is to be able to solve this problem, we have to use conservation of angular momentum and conservation of energy to basically get two equations. It's really on the edge there, to get two equations. And we need to use those two equations to algebraically figure out our V naught here. So this is kind of a tricky problem where they kind of set it up to make you do both. So it's not the nicest thing, but conceptually, like I feel like this is a really good problem to challenge your understanding of conservation of energy and conservation of momentum. So that's my time here. So I'm going to go ahead and stop this one. I will post these videos individually. If you guys have any questions, as always, feel free to shoot me a message. If you have any questions about these problems specifically, feel free to leave them on the video because then I can actually like comment to everybody. So have a great rest of your day, guys.